Okay, I want to go over the position, velocity, and acceleration graphs that you would get if you had a physical ramp in the classroom. So try to imagine a ball rolling down these various ramps and what kind of graph they would generate. So this first ramp, the ball is at rest initially, and the ramp is 50 meters long, let's just say, and the ramp is like a hill going downward to the right. So we know that when the ball is released, it's going to gain speed as it goes down the ramp. So these red arrows show you the increasing speed. So for this, the starting position is 0, and because it's gaining speed, it's accelerating. So for this particular graph, we'd have a curve going up, okay, for the position time. Now, for velocity time, it starts at a 0 velocity, and then it's gaining velocity, but it's gaining it at a constant rate. So for the velocity time graph, it would be a straight line, something like that. Now, because it's gaining velocity in the positive direction, it goes from 0 meters to positive 50, and it's a constant rate for acceleration, the acceleration graph would be on above the 0, and it would just be a straight line like that. Okay? Now, let's do the same thing, but for the ball going down a ramp, and it's going from 0 to negative 50. So now in this particular case, because it starts at 0 and it's going in the negative direction, but it's gaining speed, our graph for the position time would look like this. Okay? Now it's gaining velocity, but it's gaining it in the negative direction. So it starts at 0 and it gains it at a constant rate. So that's what that would look like, linear for the velocity time graph. And then for the acceleration, because it's gaining speed in the negative direction, straight line like that. Okay. Next, similar. The only difference here is I have it starting at 50 and going to 0. So the position is going to be a positive 50 away from the origin, but it's still going to be gaining in the negative direction, okay, because it's going backwards. So in this case, something like that for the position versus time, and then it starts with a 0 velocity, okay, so you have to start your velocity time graph has to start at 0, but it has to show gaining speed in the negative direction, right? Going backwards. So in this case, same thing like the previous set of graphs with a negative acceleration. The only difference was the starting point for the position, okay? So if you kind of look at these two, right, it's the same shape, just a different starting point. And these are also the same. Okay? So make sure you understand how those graphs are generated. Okay, the next one. All right, in this situation, I have a ramp or a hill, and what I'm doing is I'm going to give it a push, an initial push or an initial velocity going up the hill. Okay, now as it goes up the hill, it starts with a certain magnitude velocity, but as it goes up, the velocity gets smaller, smaller, and smaller because the acceleration due to gravity is slowing it down. Okay, so how do I demonstrate that? Okay, so now on the position time, this would look like this, right? The beginning of the graph, it's covering a good amount of distance over a period of time, but over the same period of time, it's covering less and less distance, and then towards the top up here, it's going to flatten out, right? Come to zero. Now, the velocity time, I have to start with some positive amount of velocity, but then it has to go towards zero, and it's going there at a constant rate. So that means it's going to be a linear slope going to zero. Now, the acceleration, because it's slowing it down, is negative. Okay, so that's how all those match up. All right, from there, the next scenario for a possible ball on a ramp, like a physical representation. Okay, what if I had a ball start at the top of a hill or ramp, initial velocity 0, I release it, it rolls down the ramp, and then it gets to a flat, okay? Well, as it rolls down the ramp, it's gaining speed, gaining speed, gaining speed. And then when it gets to the flat, it no longer gains speed, but it does have some. So what happens along the flat is it's just going to move at a constant velocity, right? So from here to here, from here to here is constant velocity. But this section is acceleration, positive. Okay, so how do I draw that on these graphs? Right, so this is just a combination of some of those shapes we had before. So now on the position time graph, all right, the curve up is acceleration, okay? Then from here on is constant velocity, okay? So it accelerates in the beginning and then has a constant velocity after that, right? So now how do I show that on the velocity time graph? Well, a slope on velocity time graph, a positive slope, is positive acceleration. Then a flat line is constant velocity, okay? So I'm satisfying both the motions in the graph now. Okay, now how do I do this on the acceleration time graph, right? So remember, in the beginning, it has positive acceleration. So positive acceleration in the beginning. Then there's no acceleration because it goes to a constant, velocity, which means no acceleration. So the rest of the time, 0 acceleration, okay? Positive acceleration, and then all of a sudden, 0 acceleration. So that's how you would show that one. Okay? Next, what if I kind of combine that shape, those two kind of hills there, right? So it starts off, it rolls down a hill, goes to a flat, keeps going at a constant velocity, and then encounters the same kind of hill but going up. Okay, so I have positive acceleration in the beginning. Okay, so positive acceleration. Then from here to here, from 25 to 100, constant velocity, 0 acceleration. And then over here, going up the hill, I have negative acceleration. Right, so I have to draw a graph that's going to show all those different parts. Okay, well, remember, curve up to show acceleration on a position time graph, then a straight line to show constant velocity, and then a curve down to show deceleration. Okay? So let me just draw it a little neater. Curve up, straight, curve down. Okay? So positive acceleration, zero acceleration, negative acceleration. All right, now on the velocity time graph, that would look like this. Linear, positive slope, flat horizontal line for constant velocity, and negative slope for negative acceleration. Okay? Now on the acceleration time graph, positive, zero, negative. Okay, last one. What if I were to shorten the flat distance, right, and just connect the two hills, right, kind of like a bowl, right? Now in this situation, put the ball here, and we're going to pretend there's no friction, there's no air resistance. We're going to do this in ideal settings. So in this situation, the ball is going to roll down the hill. As it rolls down the hill, it's gaining velocity, it's accelerating. It accelerates all the way down to the bottom. Okay, now after the bottom, it starts going up the hill, right? So it starts losing some of that velocity because acceleration due to gravity is slowing it down. So it does that. It gets all the way to the top of this hill, and then it turns around and it starts gaining velocity in the negative direction. It's repeating the pattern, but in the opposite direction. So you're going to have symmetry, right? You're going to have the same shape, but it's going to be a mirror image. So when I go to draw this, okay, on the position time graph, the first part is going to look like this. All right? Acceleration, and then decelerate, and then slowing down, okay? So let me just draw it a little neater here. So accelerating, and then slowing down. The second part of the trip, okay, it's still slowing down, and then it gains speed in the other direction, okay? It has changed direction here, right? That's the top of the hill up here. So it's changed direction. It's still slowing down, right? But it's gaining speed in the negative direction now, right? So let me kind of just summarize that again, right? So accelerating here, gets to the bottom of the hill here, slows down until it gets to the top of the other hill, changes direction, and now it's gaining speed in the negative direction, gaining, gets to the bottom of the hill again, all right? And now it's going up the other side of the hill, slowing down, all right? So now for the velocity time graph, how do I show that? Okay. So acceleration and slowing down, gets to the top of the hill, changes direction, gains speed in the negative direction, then gets to the bottom of that hill, goes up the next hill, and starts slowing down. So it would look like that. as far as acceleration time goes, we would get something that looks like that. Okay, hopefully this helps understand the physical representation of a ramp or a hill and how that would translate into position, velocity, and acceleration versus time graphs.